We will continue with the next presentation. It's a pleasure for me to present one of my grand friends, Ivan Reyes from Guadalajara. Welcome, Ivan.
Good morning, everyone. My name is Ivan Reyes. I'm a PhD student, and today we're going to talk about our recent work about robustness for image classification through adversarial sampling with a method that we're proposing that is called delta data augmentation. So this is the agenda I will be working on. And as an introduction, it is well known that deep neural networks are susceptible to adversarial and natural image alterations. Some of the most popular examples of this is the image of the left. It's an image that if you put some altered pixels in terms of the white or black, the image classification model that is related to this type of signs will be outputting some different, like a max limit for velocity. So this can lead to incorrect confidence predictions of an image classification model, and this is a very rough topic to deal. So speaking about robustness in general terms, given an input x and a function f of x, we are trying to keep the model performance in the same for each one of the x prime of the neighborhood of an x, given a distant function called delta with a maximum limit of delta. So in terms of robustness for deep learning and computer vision, this is a very common example of a panda, which we are trying to preserve the model performance under adversarial or naturally induced image corruptions. And here we are seeing a panda that the model is trying to tell us with a 57 confidence. And if we add some noise, some adversarial noise here, we are seeing the same image for our eyes, but the model is going to give us a different classification with a more confidence of this. So basically, we have the three types of robustness. The adversarial examples is the type of robustness that we are doing here in this paper. Well, but we have some other image corruptions, which is changes in the brightness or the darkness of an image. Also, we're having shiftings into the training and testing set. So for this is a common example of the pigs that with deep learning, we can make pigs fly. So this is a hypothesis of our work. What if we could extract some of the robustness from an already adversarial robust model? What we are trying here is to put some of the knowledge of our robust model to train a downstream task for classification. So this is our proposal, which is called delta data augmentation. And basically, we are trying to fetch some model A that is already pre-trained and is already robust. Let's say we are training this model in an ImageNet, a very large data set. And we are trying to apply some adversarial attack, let's say PGD. The PGD stands for projected gradient descent, and we are trying to query this model to obtain some of the deltas that were useful to treat the model. So once we have these deltas, we are using these deltas as transformations when we are trying to deal with a downstream task, let's say with a data set B, for example, CVPR10. And we will keep trying to incorporate these perturbations that were useful for a larger data set into this new novel data set, and using this as a matter of data augmentation for training a robust model B. So with this, we are avoiding to train for adversarial training to reduce the performance in terms of GPUs. And we are trying to incorporate and to reduce the gap between the normal accuracy and the robust accuracy. So for our experiment configurations, we are dealing with a model E, which is a wide breastnet 50, which is one of the top 10 robust bench models for having natural and adversarial robustness. So for this model, we are applying a PGD with ImageNet, and we are fetching and grabbing some of the perturbation that was most useful for attacking this model. And these perturbations are incorporating in terms of data augmentation, let's say here for a CVPR10. as a matter of the augmentation, and we are using ResNet 18 pre-trained on ImageNet or Model D, and basically we are testing the model in terms of the L2 norm and L infinity norm in these epsilon intensities. So for the datasets, we are dealing with CPR10, CPR100, HBHN, and the MNIST and the fashion MNIST. With these datasets, we are trying to prove that our model is sufficient good for dealing with RGB images and grayscale images. And in order to compare our method, we are dealing with some of the most popular data augmentation methods, which is the random augment, outmix, no data augmentation at all, and of course our method. So these are some results using the ResNet 18 with the L2 normal RGB images. We can see that our method for data augmentation, this is the red line, is outperforming in most of the cases of the epsilon intensities. Also, if we change the norm for L infinity norm, we are also seeing that our method is working well with the data set that is called HBHN. If we increase the size of the network in terms of the layers of the ResNet, we are using here the ResNet 50, also on RGB images, also for the dataset HBHN and the L2 norm and the L infinity norm, we are having here some outperforming performance for our method. So as a conclusion, we are here dealing with the first method for data augmentation without using of adversarial training. And we compare some of the analysis of the most used methods for data augmentation in terms of robustness. In terms of future directions for this work will be to increase the range of the robust pre-trained models. So thank you. There's some references. My name is Ivan, so thank you.
Thank you, Ivan. We have a question. We have time for a couple of questions. After this.
One question. So at a high level, what is the main difference between what you're proposing and straight up adversarial training?
Okay, with adversarial training, you are having like an overfitting for the method that you're dealing with a robust attack. Also, you're having more inference and more training consumption in terms of the model. So if you're seeing these corruptions in terms of that augmentation, you're basically running very fast in terms of the training, and you're not having this overfitting for the specific type of attack and data set.
Sorry, this is a naive question. I'm not super familiar with this space, but when you're comparing sort of your data augmentation method with others, so are you controlling for sort of the amount of extra data that you're adding? So are you adding extra data, or are you just perturbing the training?
Yeah, that's a very good question. We're adding more data in our terms of data augmentation. We're using the basic training set and also the corrupted data set with the perturbations in the same manner of the other data augmentation techniques, to be fair.
And how much are you adding?
It's the double of the size of the training set.
Thank you. One question more, Ulises?
Yes, maybe I missed something.
Yes.
What are your metrics about robustness? I only see the performance decrease with accuracy, but how do you measure actually the robustness?
Okay, yeah. In the state of the art, the most used metric for measuring accuracy is the measuring robustness is accuracy under some of the epsilon intensity attacks, which means which is the performance under these adversarial attacks. I mean, we could, in the paper, we can see some other metrics, the natural accuracy, which is only seen here is the adversarial accuracy. But this is what, if you go to the top papers about robustness, every single one is using just accuracy under adversarial attacks.
Yeah, okay. Thank you. If you have more questions regarding with this work, you can look at Ivan in the session poster. Thank you, Ivan.
Thank you.